Swayam Prabha. Digital India. Educated India.
So let's go to this demo Pytorch tensor board. So here for tensor board use, you need to use this tensor board, which is torch.utils tensor board toolkit. Okay. Now all these imports that you have seen so far, okay, and these are again some functional from Torch and Torch Vision. So these are the two important packages that we will use in this section of demo. Now the helper function, this is doing nothing but predicting the max value, okay, so that we will use. Now the CNN model is very simple, and we have seen such CNN model previously: convolution 1, convolution 2, and fully connected 1, 2, and last one, which is also one fully connected layer, and giving out features as 10, which is for your C410 dataset. We are using that same training model. Okay, so that means the 10 output feature it will actually predict, and among them for which class it is giving your maximum prediction, that will be your predicted class. Okay, so we have defined the forward function as you have seen so far in this previous demo, and we are returning the x. Now this x is actually not the prediction but output of the network. Okay, so when you are applying the cross entropy loss onto your output of this network output, then one softmax activation will be actually added. So you do not need to add any other activations after the last layer. It will automatically be added inside your cross entropy loss or whatever loss you are using. Depending on that loss, that Pytorch will decide which activations to use, and you also can define in defining while defining the losses, okay, which activations to use. Now we are downloading the data set, defining the device, okay, and again, so this is just the device which will take. This is just one for 1 GPU we are talking about for now, and then the hyperparameters. So as I was mentioning, that tensor board that we use for C or tune the network parameters, okay, so or hyperparameters, which will improve the training of or training outcome or prediction of your neural network. Now here you can see what are the hyperparameters we are using. We are using learning rate. So one range we have defined. So basically we have to see among this range which learning rate will give me better results. Okay? So this is just some definition we are using. You can use your own definition for initializing these values. So here we are actually getting this inside this list of parameters, which is kind of a dictionary where we have these key and value pairs. So key value key is the hyperparameter name itself, and the values are the tuples for these names. Now batch size, for again, if you remember, we have talked about different batch size will have different impact on the training outcome as well as the performance. Okay? So for different batch size, what kind of outcome we are getting, that we want to see. Okay? And then for the shuffle, true and false. So for training, we mentioned before when we are loading the training data set. Okay, so training data set, we mentioned that training data set you need to use shuffle equal to true. But here we are actually explicitly saying that for both we want to see, for true and false we want to see what kind of performance we are getting, because that way you will be satisfied that yes, this is these are the parameters that can give me better result, right? Now parameter values, we are defining the parameter values in this, taking all the values and storing the parameter values. So this will use for training loop. Okay. So for each combination of this, okay. So for this LR, for this batch size, for this shuffle, for this LR, for this batch size, for this shuffle, what is the outcome? Okay. So for all these combinations, we will see what is the outcome. So now we are downloading the data set. So we are actually using fashion MNIST dataset, not CFOT10 dataset. So this is also another dataset. So you can see this. This is also available in Torch Vision. So Torch Vision dot datasets dot. If you put dot, you can see what are the datasets available. We are using fashion MNIST dataset. So all the fashion and MNIST dataset that we have downloaded. And then in the training loop, we are defining the loop for all the combinations, right? So now for run ID, so for which run ID, so basically for each run it will increase. Now for each scalar, okay, for this from these param values that we have defined previously, right? So for this scalar, for the each batch size for shuffle, okay, so what will be the performance? So this model is defined to device, so it will the CNN will get transferred to the device, which is the GPU here. Then train loader will now loading the train loader using the shuffle value either true or false, depending on the value we are getting from parameters. Now the criterion and optimizer that we have defined comment just for giving output, like what kind of batch size and shuffle we are doing. Test bench summary. Now TB is essentially the summary writer, which is the tensor board writer we are defining. So summary writer we have imported the tensor board as, okay. So from the tensor board we have imported this summary writer package, which will uh, actually give you the interface to write the different images, different scalar values, different graphs. Okay, so TB is the object here. Now we are adding the images, add graph. Function will add the graph. So which add graph, the model and with the images. Okay. Now we are starting the epoch. So this for loop is essentially inside this for loop. So for each combination, we are now running this training, right? So train loss 0, correct 0. Now we have for each images batch size of images. We are doing the forward pass, then optimizing and doing the backward pass, updating the parameters. And after all the batches are processed in the forward pass, then we are actually adding what kind of loss we are with this. So now adding scalar will give you so for each epoch. So basically we are trying to plot this inside one line graph. So add scalar will add to the scalar tab inside your tensor board with all these parameter graphs. So total loss versus epoch, total correct versus epoch. So with each epoch, how the loss is improving, with each epoch, how the accuracy is improving. Okay, correctness, accuracy, all these we are calculating and updating inside the tensor board, which is the TB. Then we are printing the batch size, shuffle value, the LR value, which is the learning rate in the stochastic gradient descent optimizer, and then just adding the hyperparameters to update this. So basically, after running the entire loop, we will just close this TB, which is the tensor board. So you can see that for each run, run ID 1, 2, 3, so we are running actually for 12 times. Okay. For each time, how many batch size have been processed with each LR value shuffle. So this is just entire loop. Now from this, you can see that tracking the performance, right? So which we want to track, it is very hard. So TensorFlow will come in handy. So for TensorFlow load, so load extension tensor board and to include the logs which is inside the runs directory. So when you will run this module, you'll see that one runs directory has been formed here, okay, inside your current directory, and the runs directory actually having all the logs which you have written from your TV. Okay, so all these logs for each run will be written, and we are actually loading all the logs from runs directly. So we are log we are so this command will log all the logs from your runs directory or any other directory you are using. If you are using other directories, you just rename it. But the important thing is that you can also define which run you want to log. Okay, here we are loading all the runs. Okay, so now after running this, you will get this tensor board view here. So this display will have these images. So as you can see, the images we have loaded. So this is the fashion image load images that we have loaded from the TV writer. So just to show you, but from we loaded the images, right? So when we have written the images, the grid, we have formed the grid first, right? With this utils make grid function in the torch vision, and then this grid is added to this as images, and then the graph is also added as graph. So we will see the training module graph, right? So for the graphs, you can go to the graphs tab, and you can see the graphs are essentially compressed here. So the input is the input to your module. You can click into any module and you can see what kind of layer it is, okay, and what is the dimension. You can click onto it and it will actually enlarge. Okay, so basically it will focus onto each layer's specifications wise graph. Okay, so this is the computational graph that we are talking about. So in the first class, we have talked about the computational graph. So basically the input vectors, the weights, biases. Now if you are doing convolution operation or linear operation, which is the fully connected operation that you can do. So what kind of operation you are doing? Okay, so you can see for each layer convolution 1 to D1, then linear fully connected layer 2, linear output, and also you can see the dimensions. Okay, so at the output we are giving 10 and 10 batches. Okay, so 10 by 10 is the so in the output we have linear output. Okay, so the entire graph you can see as the graph here. So once you can analyze from the network definition and the graph actually outcome what is you are getting. So all the attributes you can see here, as well as like whether you are what kind of device, I mean in which device it is transferred. So all this structure you can see. Now, in the scalars, so as I was mentioning that the graphs are essentially loss versus your epoch, your correctness versus your epoch, the accuracy versus epoch. So all these are added inside your scalars, tv.add scalars. So now you can see the accuracy versus epoch graph. So how for each run, okay. So you can select also this run. So these are the runs. So we have renamed it with the date, the batch size, the shuffle value, and error value. Okay. So as I was mentioning that for each combination, you will get one such profile. Okay. So all these profilers we are giving output here. Okay. So that is why we have different logs here. You can see. Okay. So you can also write some expression to filter the runs also. Okay, so this is just some functionality added here. Now the hyperparameters. So the important thing I wanted to show here is that the analysis that you are seeing here is not very uh, feasible to or not very feasible to analyze properly, right? So if you have, let's say, hundreds of runs using multiple GPUs, you actually will get lost. So the HPAMs will have the inter-parameters a table view. Okay, so table view will have parallel coordinates view will have, which is very important. Scatter plot matrix view also will have. So basically in the table view for each run, how many parameters, batch size, accuracy you can see in the one piece. Okay, so this is also how you can analyze, or better way to analyze is to see the parallel coordinates view. So now in the parallel coordinates view, you can see that loss is essentially increasing, and here the accuracy, so lower accuracy to higher accuracy you are going, right? So this is the highest accuracy you are getting. Now for this highest accuracy, what is the shuffle value? What is your batch size? You can track everything, right? What is your batch size and what is the error value you can track. So for actually shuffle equal to true or false. Okay, so that those were two definitions for your shuffle, and for all the two shuffle we see that I mean you are getting very less accuracy. So for higher accuracy, you will go for shuffle equal to true. Batch size minimum is actually good here. You can see the minimum with minimum batch size you are getting good results, and the error is 0.001 for your highest accuracy for this training. Okay, so this is just the simple analysis that you can do with TensorBoard. So there are many other features that you will like to explore inside this. Go to TensorFlow, TensorBoard, and you can explore more about this. We will see a few more features of this TensorBoard in the coming classes. In the next session, we would like to go towards multi-GPU training. So we have seen that if you want to include your training or transfer your training into your device, you are actually defining this part, right? So you are defining the device, which is the device here. So you are actually transferring the model to your device and transferring the data to your device. Now we want to run. So this device is only a single GPU here. Okay. Now we will talk about how we can scale our training for multiple GPUs. So this is very interesting. This is very simple as well in Pytorch. Okay. So we have data parallel approach, we have model parallel. So data parallel approach is essentially you want to keep the model, okay, replicated into, let's say, several GPUs, but data you want to settle, right? And model parallel is the entire model you want to distribute across devices. Now there are, so as name suggests, you have actually two such libraries available in Pytorch to do data parallel and model parallel plus data parallel. Okay. So when you are doing model parallel, you can do data parallel as well, right? Because since you are distributing the model, you can distribute the data. Okay. So this is just one wrapper up to your data parallel. Now there may be different combinations of configurations that you might approach, right? So you can have single machine data parallel, you can have single machine model parallel, because in multiple GPUs you want to pipeline several models parallel execution, right? Several models parallel execution, one single model will be actually executed parallelly. You can pipeline several models training in the same pipeline, because we'll show you like how this is happening inside multiple device single model parallelly, and that way you will understand like how it will be pipelined. So this is very simple, but you just, if you see the figure, it will be fairly easy to understand. Distributed data parallel, again, data parallel in the distributed configuration setup. So where you have multiple nodes. So single node, multiple GPUs you can have, or multiple node, multiple GPUs you can have. That means multiple node, and each node may have multiple GPUs. That's what the distributed data parallel setup, or distributed setup rather, defines. Now distributed data parallel with model parallel also you can have, right? Now distributed model parallel will, so as I was mentioning that distributed essentially is one wrapper up on the data parallel. So basically you can have data parallel in the distributed, both the data parallel and model parallel, and single model parallel. So now we talk about the single machine data parallel. So now you have multiple GPUs available inside your single node. Okay, so single node here means single machine. Okay, now how you so now we are talking about data parallel. That means each GPU will be operating on multiple sets, I mean different sets of data, right? So that's why the I0, I1, I2, I3, so all these data that you are seeing, so basically your data is coming in batches. Now, depending on the number of GPUs available, you can scatter the data to your multiple GPUs. Then you can replicate your model to several GPUs. You can train all this data parallelly. You will get some loss at the end of the, so remember the pipeline that we have talked about. At the end of the training, you will get the loss. And all these losses you will gather in the master node, master GPU node, or let's say GPU 0. Okay, if you define at GPU 0, so GPU 0 node, and you will calculate the mean of these, and then actually you will compute the final loss. And then again, this process will be repeated, right? So this loop will go on depending on how many data you have and how many epochs. Doing this in, so you have seen the training pipeline. This modification only will do your data parallel activation. So basically, now we are transferring the model into, let's say, CUDA 0. Okay, so we have, let's say, CUDA 0 and 1, 2, 3, 4, okay, or 5, 6, 7. So total 8 GPUs you might have, or 4 GPUs in this case. So CUDA 0. So first model you are trying to replicate, I mean, which model you are trying to replicate, that model you are transferring to only single GPU first, and then you are applying data parallel model. And when you apply this data parallel data parallel function, automatically your model will be replicated from the GPU 0 to all our other GPUs. And depending on the number of GPUs available and the batches you are fetching, it will actually segregate or scatter the data into your GPUs. So this is very simple. Now, single machine, multiple model parallel. So, sorry, single machine, single model parallel. Okay, we are not yet talking about multiple models. Okay, so just stay with single model now. So we have several stages of pipeline. I mean, several stages of the training pipeline. You have seen that, right? So, what are the pipelines you want to, let's say, execute in which GPU? You can define that, and depending on that, your data synchronization will happen. And in the end of all the sequences are happening, then you can actually compute the loss. Now, when this sequence is happening, at that point of time, you can actually feed through a different layer of different model into the first GPU while it is doing the second sequence of the first model. Okay, so this is how you can pipeline. But basically, this is the code part will parallelize the model execution into different GPUs that you might have. So here, let's say we have 2 GPUs. So we are gathering those GPU IDs into GPU 0 and GPU 1. And then we are actually transferring these models, defining these layers. So this is just a simple definition of the layer that we want to execute in which GPU. So transferring the sequences of the training into the GPUs. Okay, then we are doing the forward pass. Now, which net will be executed in which device? You can just transfer it into that GPU, and that's it. So once you have defined, like, this model is essentially running in, let's say, 2 GPUs. Okay, so this is very simple. So these are the upgradation of the entire training pipeline that you have seen that needs to do that to enable this model timelines. You can also distribute data parallel. So basically, now we are talking about distributed data parallel. Okay, so that means you have several nodes with multiple GPUs, right? So machine 0 has, let's say, 2 GPUs. Machine 1 has 2 GPUs. GPU 2, GPU 3. Now, what we are doing here, so in the data parallel, we have seen that that model will be actually replicated into several GPUs, and all the data will be scattered and feed to the GPUs and processed on the computer. So this data parallel approach is again very simple to parallelize, because once you have defined multiple GPUs in multiple nodes, so let's say we have 2 nodes here, 0 and 1, and with 0 and 1 and 2 and 3, which is the definition or IDs of the GPUs for each machine, we are creating this list here. Okay, so basically you need to define the rank also, because the number of rank will define how many processes will be created or the replicas will be created. So basically, to avoid GIL, so which is the global interrupt lock, because actually you need to synchronize in each round of loss computation. Okay, so that's why how many number of GPUs you have, those many number of ranks definition is the thumb rule. So then you can define the model to the GPU 0, because from the GPU 0 actually it will be replicated to other GPUs when you will define this nn.parallel.ddp. So DDP is essentially the data parallel distributed data parallel library. Okay, so then we can actually use this model and these devices. Okay. So this is just the same as data parallel. You can see one wrapper up of data parallel approach. Okay. And then you have training loop, and for each machine rank in the word size. So word size is essentially the total number of processes in all the machines, and rank is the total number of processes in each machine. Okay, and depending on that, it will actually create multiple threads and the so this is just to fork and join your processes, but ultimately your code for training will differ this much. Okay, so text, which is the distributed data parallel with model parallel. Okay. So again, multiple nodes we have. So these multiple nodes having multiple GPUs we have seen. And if you remember the model parallel in a single GPU, okay, single machine, multiple GPU. So, 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 so you have defined which layer actually. So let's say subnet 1 and subnet 2 are the two sequences in your training module, and let's say they are simply fully connected layer. Okay, for simplicity, we are taking fully connected layer. Now, which layer will go to which device that we have defined? So basically, GPU 0 and 1 you have defined, but you have made available these sequences to those GPUs because you want to parallelize the model execution to GPUs. And also, when you are doing the forward pass, you need to also get the data available for that, because you can see the output of the this layer is going to the input of this layer. So if you do not give y as the input to the second layer, which is the GPU1, because your next layer is being executed in the GPU1, so this pipeline you need to set up. So this is what I was talking about when you were trying to replicate, when you were trying to parallelize the model execution. in accordance with defining which layer will go to which GPU, which data also will go to which GPU. It will you need to define it properly, otherwise you will have wrong loss computation. Okay. Now we are talking about the data parallel as well as model parallel. Okay? So in multiple nodes, you have multiple GPUs. In one node, you are trying. I mean, in all the nodes, basically, you are trying to parallelize the model execution with parallel data. Okay? So that is why, again, you can see that data parallel is always there with distributed model parallel. Okay? So this is the inherent uh, 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 functionality that distributed data parallel will use. Now, when you are trying to define this, because let's say you have GPUs in 0 and 1 node, you have in 0 node 0 and 1 and 1 node 2 and 3 with this machine rank. Now you have converted your model into this parallel, and this is the training loop which will run. Okay. Now, once you are working with DTP, okay, not the data parallel, right? So again, just to make sure that you remember this part. So this is actually we are not using the distributed data parallel. Okay? So this is just we are transferring which model sequence will go to which GPU. Okay, so we are not using any defined library. Okay, now here once we are using DTP, when you are transfer, so that time we needed to define which sequence will go and how the output and input will make the connection between different GPUs outputs and inputs. But here, since you are using DTP, torch.mn.parallel.dtp, you do not need to define that. You just uh, it will just take care of all the data parallel scatter. So basically, what it will do, it will scatter the data according to different replicas of the model, and different replicas of the model will have different sequences allocated to different GPUs inside one. Okay. And then how many processes? These are the standard process spawning. Okay, so this will be used. So this is how you can just scale your training entire pipeline that you have seen so far with the use of these two libraries. One is the data parallel library and one is distributed data parallel library in Pytorch. There are also other libraries and other packages available you can use. So once you know actually the basics of these two libraries, there is also RPC, which is remote procedure call uh, from Pytorch. So basically, we will not have the bandwidth to discuss that package, but you can go to pytorch.org to get details of that package as well. But apart from the standard packages that is available with Pytorch, so all these are developed by Facebook, and also the development is continuously getting updated. There might be a few bugs in the previous versions. Next version will come up with the fixes. So all these things you will see, but there is a strong community available for that, and you can actually also contribute if you want to for developing these libraries. So this is completely open source project. And apart from that, that I was talking about, there is also some third-party libraries that is using wrapped PyTorch modules to abstract more of these tasks even in fancier ways. So that also you can see in many other uh, libraries. So few of them maybe we will discuss in the next class, but this class will conclude here. And for the code, you can go to this uh, link for getting access to one very, very intuitive uh, implementation of that data paradigm. So basically, we have seen how to actually tweak your entire training with just few lines of code to make it available to multiple GPUs. So one such example is there in this code, which is available in this link. Thank you for today. We'll now go towards the question and answer session.